Okay, so we have arrived to lecture 20, net areas of the polyhedral, and as we can see here, we have basically the same polyhedral we studied last lectures. And our objectives will be apply the decomposition of polyhedral, define the areas of the parts of the polyhedral, and determine the net area of the polyhedral. Okay, so the first shape that we have of the first polyhedral we have is the cube. And as we mentioned in the previous lecture, the cube is made out of 6 squares, okay? And if we remember the characteristics of the square, it has all sizes are the same and they form 90-degree angles, okay? So basically, how we calculate the net areas is by calculating the area of each face and then add them up, okay? So how do we know the net area of a cube? We know that it has 6 faces and each face is a square. Okay, so basically we calculate the area of one square and then multiply it by 6, right? To get the net areas of this polyhedral. Okay, so if we will open this cube and put it in a 2D plane, in a flat surface, right? Like we take this edge, this edge, this edge, and this edge, and we just open up, it will look like this. Okay, so here we have basically the composition of the cube when we open it up and put it in a 2D plane. Let's see if this face is 1, right, which is this face over here, the one that we're seeing, then the one next to it will be 4, and the one next to 4 will be 6, right, because we're going this way, 1, 4, 6, then next to 6 will be 2, right, and 4 is also attached to 3 and 5, right, so 3 will be at the bottom and 5 will be at the top. Okay, so again we have 6 squares, and remember the formula for the area of square, is this side square, or you can say also base times height, which for the square is the base and the height is the same, so you just say the side square. Okay, so the net area for this cube will be, the area for the cube will be 6 times the area of each individual square. So 6 times L square. Okay, so let's move on to the next figure. We have the tetrahedron, and if we remember the last lecture, we said it is 4 triangles, 1 at the base and 3 that meet at a common point, right? So the net area of the tetrahedron will be the sum of the triangle's individual area. Okay, so let's say that if we want to open up this tetrahedron the same way as we did for the cube, how would it look? Okay, so it will look like this. Here we have the net areas of the tetrahedron, and we can see we have 4 triangles. The triangles don't necessarily need to be equal in size, only these 3 need to be equal in size, so they can meet in a common point, but they don't have to be equal to this one. And basically will be that the net area of the tetrahedron is the sum, this is a symbol of sum, the areas of individual triangles. Okay, and if we remember, the area of a triangle is base times height divided by 2. We need to apply this area formula to each individual triangle and then add them up to get the net area of the tetrahedron. Also for the tetrahedron, we have the the regular tetrahedron, that it is composed by 4 equilateral triangles. Remember that equilateral triangle is that all sides are have the same length, so you basically have 4 equal triangles, but that's the regular tetrahedron. Okay, so let's move on to the rectangular pyramid. And remember, last lecture we took a rectangular pyramid. It has a rectangular base. Okay, so here we can see that the base where all these triangles meet is a rectangle, it's not a triangle. Okay, so if we want to calculate the net area of a rectangular pyramid, we need to calculate the areas of the triangles that are in this pyramid and the area of the base, which is a rectangle. Okay, so first of all, let's open up this polyhedron and see how it will look like in a 2D plane. Okay, so the rectangular pyramid, when we open it up, looks something like this. Remember that this face right here is congruent, right, in size with this one here, and this one here is congruent to this one right here, right? So that means that if I take one face and put it on top of the other one, it's exactly the same size. So, okay, so we have 2 pairs of the same triangle and 1 rectangle. How do we calculate the net area of the pyramid? It will be, first, the triangle in yellow will be base times height divided by 2, and this one we're going to multiply it by 2 because we have 2 of them, plus the one in green will be also base times height divided by 2, then multiply by 2 because we have 2 of them, and finally the rectangle that is the base, it will be base times height, and we only have one. Okay, so again we have the area of one type of triangle multiplied by 2 because we have 2 of them, plus the area of the other type of triangle multiplied by 2, plus the area of the base, which is a rectangle. Okay, so let's move on to the next page. Here we have a cylinder, and if we remember the last lecture, we said that a cylinder is composed by 2 circles, the one at the top, the one at the bottom, plus a rectangle around the edge of this circle. Okay, so let's break this figure apart and put it in a 2D place. It will look like this. Okay, so we can see here how the cylinder will look like. And how do we calculate the net area of this cylinder? Okay, so we have 2 circles. The area of a circle is pi r squared, and we multiply it by 2 because we have 2 circles, one at the top and one at the bottom, plus the area of the big rectangle, which is base times height. Okay, so again, the cylinder is composed by 2 circles, one at the top, one at the bottom, and one big rectangle around the edge of the circle. So we add all of these areas together and we get the net area of the cylinder. Okay, so let's move on to the last shape, which is an hexagonal prism. And again, we know that an hexagonal prism is made out of 2 hexagons, one at the top and one at the bottom, and multiple rectangles join each side together. Okay, so how do we calculate the net area of the hexagonal prism? This is a little bit more complicated because the area of the hexagon can be represented as 3 square root of 3 divided by 2 times the side square. Okay, so this is just the area of an hexagon, right? So one of these faces. So what we need to do to get the net area, it will be 2 times this equation of the hexagon plus the area of each individual rectangle joining each face. Okay, so remember, for a regular hexagon, all sides are equal in length, which means that all rectangle joining are the same. So if we have the height of this hexagonal prism, then we can multiply by the side of the hexagon. Let's call it A, one side of the hexagon, right? We already used A in the hexagon area. A times H, and then multiply by how many rectangles. If the hexagon has 6 sides, we have then 6 rectangles, right? So we multiply by 6. Again, this is a little bit more complex. We have the area of the hexagon is this one right here, but we have 2 hexagons. We have one at the top and one at the bottom. So we multiply by 2, right? So already we have the 2 areas of the hexagon plus 6 times the area of each individual rectangle joining each face of the hexagon. It will be right here. Okay, so it's basically getting this information and applying this formula to get the net area of an hexagon. Okay, so this is the last example that we have for today.